Number 6, relationship with system linearity. Relationship with system linearity again follows very similar principles as in the case of the differential equations. The system is linear with respect to the input if all the auxiliary conditions are 0. That is because again it is convenient and it is very informative to represent the complete solution as a sum of a response to the auxiliary conditions plus a response to the input. So, we will do that again here and write y n equals y a n plus y I n, where the notation will carry the same meaning as we had at the previous occasion, right. So, now we have this, then it becomes abundantly clear that y I n is linear with respect to x n, the input. So, that in place of x n, suppose I apply x 1 n plus x 2 n, or even more generally suppose I apply say b 1 x 1 n plus b 2 x 2 n, where x 1 n yields y a n plus y I 1 n, and x 2 n yields y a n plus y I 2 of n. Then the response to b 1 x 1 n plus b 2 x 2 n will be y a n plus b 1 y I 1 n plus b 2 y I 2 n. Clearly, this entire thing taken in one piece is not linear with respect to the input, but this part which corresponds to the pure input response is linear with respect to the input. Likewise, y a n will be linear with respect to the auxiliary conditions. If all the auxiliary conditions are uniformly scaled by the same factor, say c, then instead of y a n you will get c times y a n. Common factor c, so that you have a response, well then the response due to the state alone that is to say the 0 input response will become y a n times c. Thus, keeping the input the same, if we keep the input at x n and scale the auxiliary conditions, we would get y n equals c times y a n plus y I n, which taken as a whole again is not linear with respect to the auxiliary conditions either, but this component taken alone is linear with respect to the auxiliary conditions. Just like in the previous page, this component alone was linear with respect to the input. It is always the other component that spoils the linearity. Okay. So, this more or less summarizes our discussion of the relationship between the linearity of the differential equation and the linearity of the system. Having understood all this, we will just make one closing comment. The presence of the auxiliary conditions and the effect they have on the linearity of the system with respect to the input is sometimes captured by some authors using a term called incremental linearity. These comments I am about to make will apply equally for the continuous time and the discrete time systems. The argument they make is the following. Suppose you have x1t as a possible input and x2t as another possible input, and the corresponding outputs are y1t and y2t. What they claim is this: let us not look at whether the output y1t or y2t is linear with respect to the input x1t or x2t. Let us instead ask whether the difference between y2t and y1t is linear with respect to the difference between x2t and x1t, right. This is a very interesting way of posing the problem. What we are saying is, let us pretend that we have this system and the input is x1t minus x2t, so that the corresponding output is y1t minus y2t. Then they claim that systems which are subject to auxiliary conditions, whose linearity is now hostage to this term over here, which prevents it from being linear with respect to the input, such systems will still be incrementally linear. That is to say, y2t minus y1t will be linear with respect to x2t minus x1t. This is easily demonstrated. All we have to do is go over here and write what happens when you apply the input x2t minus x1t. By the linearity of the system, the response should be the corresponding combination of the individual responses. So, for x2t you had y2t as the response, x1t you had y1t as the response. So, let us write x2t yields y2t, which is basically ya of t. Ya remains the same because it is due to the auxiliary conditions, the inputs alone are being changed, plus yi2 of t. x1t will yield y1t, which is ya of t, again the same ya of t, plus yi2 of t. So, x2t minus x1t would give you the difference of these two expressions on the right side, where yat would automatically vanish and you would just get yi2 of t minus yi1 of t. Clearly, if you scale this by a certain factor alpha, for example, this would also scale by the same factor alpha. We must realize that this linearity we have just spoken of is really not the linearity of a system with respect to input and output. It is more precisely the linearity of the system with respect to increments of the input and the output. So, let us just put this down as a closing comment. Not with respect to the input output pair, but rather with respect to the pair of increments in the input and output. So, this closes the discussion about the linearity properties of systems described by linear constant coefficient ordinary difference equations. The next step, of course, going along the same lines as we followed in the case of the differential equations, linear constant coefficient ordinary differential equations, is to study the time invariance properties of the system vis-a-vis the properties of the differential equation, difference equation which describes it. So, let us look at that next. Again, we only proceed by analogy. We do not start a discussion from the fundamentals. We only go by analogy with the corresponding study for the case of the differential equation and show how practically the same results can be modified to get the corresponding results for this case. Time invariance again is the property by which the output shifts along the time axis by the same amount that the input shifts. So, if x n yields output y n, then any discrete time invariant system will satisfy x n minus n naught must yield y n minus n naught. So, this is the property we are looking for. We are essentially going to ask the question, what should we do, what should we ensure in order that a system which yields this input output pair also yields this input output pair for all values of n naught. One second please. Okay. The answer, as may be expected, is very similar to what we had for the case of the time invariance of the continuous systems described by differential equations. It is simply the following: when you shift the input, shift the reference time at which the initial conditions or the auxiliary conditions are given also by the same amount. In short, what we are going to say is, if the system yields for input x n the output y n, then and the auxiliary condition was y 0, which was essentially y at y of n at n equal to n 0, which would be the case for a first order system which requires only one auxiliary condition. Then if we shift the input by a certain quantity nu, let us say that instead of x n we apply x n minus nu, where of course nu must be an integer. Then in order for this to result in y n minus nu, this condition which we have applied over here must now be the same value y naught, but it must apply at y n minus nu at n minus nu equal to n naught, that is to say at n equal to n naught plus nu. If we ensure this, then the output will indeed be this quantity. Now, going further to generalize for the case of higher order systems described by higher order difference equations, it is simply this: all the time instants at which the different auxiliary conditions have been specified must be shifted by the same amount, namely nu, in the same direction as the input has been shifted. That is to say, if you had, let us consider the case when only points have been given at capital N different places, that is to say, let the set of initial conditions, let the set of n auxiliary conditions for an nth order system be in the form y01 to y0n, which are essentially respectively given by y n at n01, y n at n02 and so on to y n at n0 n. This is the initial case. With these initial conditions and let the input be x n for an output y n. This is the first part of the formulation. Now, let us say let the input be replaced by x n minus nu. If the input is replaced by x minus nu, x n minus nu, we can now say that then the output will be compatible with the time invariance property output will be compatible with the time invariance property and thus be equal to y n minus nu if but not only if it is just a sufficient condition that we are providing here. It is not a necessary condition, as was the case in the discussion on differential equations, the time invariance property in relation to differential equations also. We are only providing a sufficient condition here. If the new auxiliary conditions are y01 onto y0n evaluated at respectively y n at n minus nu equal to n01, y n at n minus nu equal to n02 and so on to y n at n minus nu equal to n0 n. So, the values remain the same, but these values should hold at n equal to n01 plus nu, n equal to n02 plus nu, n equal to n0n plus nu respectively for y01 to y0n. If this sufficient condition is met, then we are going to actually observe a shifting of the output just in the manner that the input was shifted, by the same amount and in the same direction that the input was shifted. But again, there are other ways of specifying it. instead of shifting the points at which the auxiliary conditions are specified, you can instead shift the auxiliary condition values that you expect to find at those same instants that you used earlier. In fact, instead of using n minus nu equal to n naught, that is to say n equal to n naught plus nu, or n equal to n01 plus nu, n equal to n02 plus nu, you can stick to the same time instants, but then you should give the correspondingly shifted values. That is to say, you should alter the values appropriately. You could, for example, you could alternatively remain at the same instants n01 to n0n, but then the auxiliary condition values y01 to y0n would change to y dash 01 to y dash 0n, right. What are these values y dash 01 to y dash 0n? They are the values you would see for the curve after it has been shifted. So, finally, let us look at the issue of causality. We only had a cursory discussion of this when we dealt with the differential equation, and in fact, I said at that time that this issue of causality would be better explained in the case of the difference equation, and that is why I promised to postpone this discussion to that time. Well, now the time has come. Causality and the differential or the difference equations. All right. Before I actually plunge into this discussion, let me just go through a brief exercise. For the case of the difference equation, let us in fact handle the simplest of possible cases, the first order difference equation. Is there a way to find the impulse response of the system from the difference equation? This is the question I will raise. So, let us try to answer this question. Suppose we have, let us take a very concrete example. Suppose we have a difference equation like yn plus alpha y n minus 1 equals x n. Suppose we have this. Can we find the impulse response of the system from this? On the face of it, our experience, our intuition, everything tells us that this must be a causal system, and we also know that we are free to replace the independent variable over which these signals are given by some other quantity. Thus, for example, if yn plus alpha yn minus 1 equals xn, we are perfectly right in writing yn minus 1 plus alpha y n minus 2 equals x n minus 1. and so on. We could write this for whatever amount of time shift we wanted, we could rewrite the equation like this and it would still be valid. All right. Now, I am going to proceed as follows. I am going to write this original equation as y n equals x n minus alpha y n minus 1, which equals x n minus alpha. What is y n minus 1? Y n minus 1 can be found from this second equation over here, this one, by just rearranging the terms and writing that y n minus 1 equals x n minus 1 minus alpha y n minus 2. So, that is what we are going to replace for this over here, and write y n minus 2 equals, we already have y n equals x n minus alpha y n minus 1. So, again we would write alpha over here and then write in brackets x n minus 1 minus again alpha y n minus 2. You can do one more round of this and you would get that this equals x n minus alpha x n minus 1, fine, minus alpha, what is y n minus 2? It would have the same form as y n minus 1 that we have written over here, except that all time instants would be shifted again by one further point. So, you would get x n minus 2 minus alpha y n minus 3. This is what you would get. Now, in principle you can keep on doing this, and every time you do this an additional term would appear and you would keep pushing the time instant y on the right side further and further away. You could keep doing this indefinitely, as I said, and so ultimately what will you get? You will just get a sequence of terms on the right which involve x. Let us see the terms that we have already collected. They are x n minus alpha minus alpha x n minus 1 plus alpha squared x n minus 2 minus alpha cubed x n minus 3 and so on. Now, can we find a compact expression for this, a compact formula for this? I suppose we can. On the one hand, you have all the members of the x sequence, x n minus 1, x n minus 2, x n minus 3. Then you have alpha to the power 0, alpha to the power 1, 2, 3 and so on. So, in general you have something of the form alpha to the power k x n minus k, fine, but the sign, there is a problem with the sign. The first term has a positive sign, the second has a negative sign, the third has a positive sign and so on. So, what we really should do is to get a minus sign for the second term. We again see that that is the place where k is equal to 1. So, we will just write minus 1 to the power k. This is the general form of any typical term, but we need the summation of all these terms. So, let me just rewrite this to get the final form of the relationship between y and x expressed purely in terms of x, a recursive equation in terms of x is equal to the summation as k goes from 0 to infinity minus 1 to the power k alpha to the power k x n minus k. Now that you have this relationship between output and input, where the output has been exorcised from the right hand side, you can apply the definition of impulse response. Definition of impulse response: let the input, the definition is let the input be the discrete impulse delta of n and the output will be h of n. So, let us do that over here. You had y n on the left side, that would become h n, and on the right side you will just get minus 1 to the k alpha to the k delta n minus k summation. H n minus alpha to the k delta n minus k. So, this has given us the impulse response of the system starting from the difference equation that we had over here. This was the difference equation. If you look at the form of the impulse response you have, you clearly see that the present value of h n depends upon a lot of past impulses, that is, consists of a lot of impulses that occurred at various points in the past, n minus 0, n minus 1, n minus 2, n minus 3 and so on. In short, you have an impulse response which is what is conventionally called causal. You will have a sequence like this. Minus 1 to the alpha k delta n minus k would give you an impulse response that is maybe like this. This would be h n. And this indicates a causal impulse response, because h n equals 0 for n less than 0. Fine. So, this is fine. Does this mean that the difference equation inherently implied that the system was causal? This is the conclusion that most of us would come to. Let me just rewrite the difference equation once again that we used. We had y n plus alpha y n minus 1 was equal to x n. If we go back to this equation, we can probably trace what we believe is the reason why this system is causal. We will say that y n recursively depends upon y n minus 1, where y n minus 1 represents a point of the output to the past of y n. Since you have y n minus 1 over here, clearly this must be a causal system. But I will put a question mark on this. Is this really true? And in order to turn the whole thing upside down, let me make some very simple changes in the way this differential equation has been written. Instead of n, I will write n plus 1. So, I will get y n plus 1 plus alpha y. Now, n minus 1 becomes n because I have added 1 to the time variable at all the points, plus alpha y n equals x n plus 1. So, this is the equation I have. Now, let me transform it suitably to get an expression for y n. What will I get? I get y n equals 1 by alpha x n plus 1 minus y n plus 1. Fine. Already over here, where I rewrote this equation, you would begin to wonder, wait a minute, is this an anti-causal system all of a sudden? Because clearly now y n is present over here in this term, but it seems to depend not on y n minus 1 as it did before, but on y n plus 1. That means to say it depends recursively not on the past input, not on the past output, but rather on the future output. In order to explicate this further, let us again go through the same exercise of extracting the impulse response for the system. We have this form over here that we will repeatedly and recursively use. We have y n equals 1 by alpha x n plus 1 minus y n plus 1. In this, we will replace y n plus 1 by an expression for y n plus 1, just like we did last time. Y n equals 1 by alpha x n plus 1 minus, what is y n plus 1? The expression is the same, just like you have over here, just like you had over here. You have y n plus 1. If you wrote y n plus 1 on the left hand side, you would get 1 by alpha x n plus 2 minus y n plus 2. So, let us write that over here, minus 1 by alpha x n plus 2 minus y n plus 2. Now, we are going to handle this in another round to get 1 by alpha x n plus 1, fine, minus 1 by alpha x n plus 2, fine, minus y n plus 2. What is a y n plus 2? It will be equal to 1 by alpha, open brackets, x n plus 3 minus y n plus 3. Right. So, this is what it looks like. You could keep doing this until eternity if you wanted, but already the pattern has begun to emerge. Let us just expand these terms. This is equal to 1 by alpha to the multiplied by x n plus 1 minus 1 by alpha squared x n plus 2 plus 1 by alpha cubed x n plus 3. Again you would get minus 1 by alpha to the power 4 x n plus 4, so on. You would get terms like this. Now again it is important for us to put this into a proper compact form, get it into a formula, because that makes us see things more clearly. So what is this? You have x n plus 1, x n plus 2, x n plus 3, x n plus 4 in consecutive terms. So that part is straightforward. You have 1 by alpha minus 1 by alpha squared plus 1 by alpha cubed 1 by alpha to the power 4. In fact, with x n plus k you have 1 by alpha to the power k. Fine. Finally, the first term has a positive sign, the second term where k is 2 has a negative sign, and so on. So, I could write this as summation k equals 1 to infinity 1 by alpha to the power k, then I have minus 1 to the power k minus 1. This is the only way I will get the even terms to have a negative sign. By even terms I mean terms containing even values of k, and then I have x n plus k. This, if you plot this, you would get an expression that goes this way, without prejudice to what choice of value we take for alpha. Let us say that alpha is equal to 2, then 1 by alpha is equal to half, and you would get a sequence which diminishes for larger values of k, diminishes in magnitude, but alternates in sign, because there is a minus 1 to the k minus 1 over here, and the first term starts with k equal to 1. So, you would get maybe a term like this and a term like this and something like this and something like this and something like this and something like this. This is what you would get. Clearly now it appears that well, this is a little premature, so let's just take this all the way and write the impulse response first. Impulse response for this you set x n equal to delta n, then you would get h n equals summation k equals 1 to infinity minus 1 to the power k minus 1 to the power k minus 1 divided by alpha to the power k x n plus k, which is what I was trying to plot actually. Hn. So, now it appears Hn is anti-causal. Look at that. Same equation in the previous page gave you an Hn which looked causal. Hn looks causal over here. Where is that expression for Hn? Yeah. because h n is 0 for n less than 0, whereas here clearly you have h n equals 0 for n greater than or equal to 0. This is what you have over here now. So, it appears to be anti-causal over here, very much in contrast with what we just discovered a little while ago. Now, what can we say about this? Is either this derivation wrong or was the previous derivation wrong? The point is that neither was wrong, both were right, and in fact that is the most important thing we have said in the last few minutes. Both are right. The difference equation alone is neutral with respect to the direction of time, the point that I made long ago, but did not substantiate until now. The way I have done it with an example over here is a sufficient indication that the differential equation or the difference equation is neutral with respect to time. You could solve it with towards positive time, you could solve it towards negative time. It has itself no preference for direction of time. That is as far as the mathematics is concerned, as the mathematics of the difference equation is concerned, or the mathematics of the differential equation is concerned. We have given you a demonstration here of how the same equation with the slightest of changes can be made to look like a causal system describing a causal an equation describing a causal system, or an equation describing an anti-causal system. You could make it look either way. You could go ahead and actually derive the impulse response, which could also look causal or which could also look anti-causal. The fact therefore is that what you want to do depends upon your choice, pretty much like the case of the auxiliary conditions, where it was additional information about the physical system that compelled us to, or that helped us to pick the correct solution out of possible solutions. Here again you can say you have multiple possible solutions, you have causal solutions, you have anti-causal solutions. Which one do you want? The answer again has to come from the outside world, from the world outside the equation itself, and the answer that comes is this: as far as one is concerned with real physical systems as a physicist would use the word physical, certainly we cannot have an anti-causal system, because there is no way you can predict the future. You cannot anticipate what the value of the output is going to be at a future instant of time. You cannot certainly anticipate what the value of the input is going to be at a future instant of time. So, actual systems that you can implement, be they continuous systems that you implement with capacitors, inductors and resistors, or discrete systems that you implement with shift registers and adders and multipliers and so on, both these kinds of systems would be hostage to the fact that the real world around us is causal. So, it is the causal solution that you would choose, but it is always important to keep in mind that you are only choosing this by conscious choice. The theory has no preference for direction of time. It could be this, it could be that. There is no problem either way. Fine. So, this completes our discussion of causality and its relationship to the differential equation that describes the system, both as I said for the continuous differential equation case as well as for the discrete equation case, the discrete time difference equation case. Causality or anti-causality has to be chosen by us depending upon constraints of the actual system. The important thing is that there are some situations in modern signal processing where everything is done completely by software. You do not have capacitors and inductors anymore. You just have an array of data completely available. The entire input data is available for all time, from the starting instant to the closing instant, before and after which we will assume there are only zeros in the input data. You have the entire array given to you, and if you this entire array is given to you and you are asked the question whether the computation that is involved as described by a differential equation or a difference equation is a causal computation or not. You could say, look, I could construct a computation which is causal, I could construct a computation which is anti-causal. Since all these are just numbers which are being taken in and out of the memory of a computer, it really does not matter. You can compute the performance, the output of an anti-causal system just as easily as you can compute the output of a causal system, because it is an artificial world anyway, it is a virtual world, it is the world of the computer, you could always do it either way. So, while the actual physical world around us is compelled to be causal, that is not really true with the virtual world around us. It is possible to find pockets of, or to construct pockets of an anti-causal universe inside our computers. And so, all this theory, which until the time computers were widely available for simulation and computation, until that time all this theory was considered to be unnecessarily general, dealing with possibilities which had no physical meaning, no longer true. These possibilities too can be exploited under certain situations. You can actually make an anti-causal filter, you can actually make an anti-causal system to do certain things. Now that we have more or less left the difference equations and differential equations behind us, let us just carry the essence and not the details.